So, analysis of a mechanical system is little complex in the laboratory. As we have seen, the components of mechanical system are mass, spring and friction component dashpot. So, you are aware that application of voltage to an electrical circuit and varying the parameters like inductor, capacitor, resistance is quite easy, whereas varying friction, varying spring stiffness in mechanical system is slightly difficult. As I was indicating that the purpose of analysis is to study the characteristics of an existing system so that you can modify that to design a better system. So, the given mechanical system can be converted into an electrical system, then do whatever modifications you want and bring back that system back to mechanical system with modified values. It is always good because electrical laboratory varying passive and active components is quite easy compared to mechanical system. So, thanks to all systems, every system has a passive components and active components, and there exists some relation between electrical and mechanical parameters. So, the transformation from mechanical system to electrical systems is easy. We have seen in electrical circuit the main components are resistor, inductor and capacitor, and application of voltage to that R, L, C, and there is a current that actually flows when voltage is applied. In the case of mechanical system, we have seen just now that it is associated with some mass, then a force is applied on it, then there are reaction forces that exist, one due to spring and the other one due to friction, and this has a displacement of x, it has a velocity and acceleration. So, as you know that we can have the voltage equation according to Kirchhoff's voltage law here, V is equal to R I plus L di by dt plus 1 by C integral I dt. And here according to Newton's second law of motion, F is equal to m d square x by dt square plus b dx by dt plus kx. Now, as you can see, it is a second order differential equation. I can transform this equation also into second order differential equation by replacing current I equal to dq by dt. Then I apply in this, I can get here L d square q by dt square plus R dq by dt plus q by c. Now, this is also a second order differential equation of an electrical system, and this is for mechanical system. Now, you can compare these two, both are of similar type. Now, you can generate good number of analogous terms between electrical and mechanical system. So, let us see with the help of these two equations what is the item and what is that electrical term and what is the mechanical term that is analogous to this electrical term, so that you can convert the given mechanical system into electrical system, do whatever modifications you require to give a better output, then convert that system back into mechanical system. So, the item, okay, I write as a independent variable in the given equation. In electrical term, V, voltage is the independent variable. I can apply the voltage to this electrical circuit, and corresponding analogous term in mechanical system, it is a force. That's why it is called force voltage analogy, because force in mechanical system is analogous to voltage in electrical system. Sometimes voltage is called a driving force to drive the current in an electrical circuit. It's like a force in mechanical system. Now, what is the dependent variable? Dependent variable here in electrical terminology, current or charge. So, I say current is a dependent variable and charge is also dependent variable. What are the corresponding terms there? Displacement and velocity. So, velocity and displacement, they are analogous. Displacement in mechanical system is analogous to charge. Next, the passive components in that storage components. As you know, in electrical system, inductance is a storage component, energy storage component. Energy is stored in the magnetic field. That inductor L, what is the corresponding term in mechanical? You can see that m d square x by dt square is corresponding to L d square q by dt square. So, mass is similar to inductor of electrical system. And the another storage element is a capacitor here. So, it is given in the denominator actually 1 by C into Q. So, there it is K. So, I can write here the reciprocal of spring constant, spring stiffness coefficient is similar to the capacitance. And dissipative element, as you know, resistor is a dissipative element. Energy is dissipated, it can be never taken back, whereas inductor and capacitor are of not like that. They can take the energy from the source, but they give back to the required system. But resistor is a dissipative element and energy cannot be taken back. So, resistance in electrical system, you can see here R dq by dt, here B dx by dt. So, the dash part or the friction component is the corresponding analogous term in mechanical system. Now, what is the law that is associated to write equations in electrical system is KVL. What is the law? The term is the law associated to develop the equation here KVL, and here sigma force equal to 0, that is Newton's second law of motion. Okay. So, the law associated to electrical system is KVL and here Newton's second law of motion. So, that way you can have an analogy between electrical and mechanical systems, so that you can transform the given mechanical system into electrical system. For any modifications can be done and bring that system back into electrical system, mechanical system. As we have discussed in the previous section, that force voltage analogy helps the given mechanical system can be transformed into electrical system, because varying any parameter, may be passive or active, is very easy in a given electrical system. So, do whatever modifications you want to do, then transform back into mechanical system. Another analogy is developed for our convenience, force current analogy. So, the force equation in a mechanical system, you are already familiar with this acceleration term, velocity term and displacement term. In the case of an electrical system, now we consider all the three components are in parallel to the current source. All the three components are L and C, and say the voltage is V here. Now, what is the equation actually you can have here? Because I have already equation for mechanical system. So, I need to have an electrical equation also, because I want to have a analogy between force and current, not voltage. In the case of previous section, force voltage analogy, so I have considered series RLC circuit. Now, I consider parallel circuit and I apply KCL. I apply KCL here to write this equation. So, I of t is equal to V by R plus 1 by L integral V dt plus C dV by dt. Current in individual components, sum is the total current. Now, as this is a second order differential equation, I would like to have this integro differential equation also into a differential equation. So, as you are aware, according to Faraday's second law of electromagnetic induction, V is given by rate of change of flux linkages. So, d phi by dt or d xi by dt, we write, assume that n is 1. So, voltage is given by d phi by dt and substitute that here to get a second order equation. For comparison, it will be easy. So, you can write here now C, I am replacing V by d phi by dt here. So, d square phi by dt square, you have first term, and this one 1 by R d phi by dt and 1 by L into phi. Yes. Now, you can compare this is current I and this is force. So, you need to compare these two equations to develop force current analogy. So, any given mechanical system you can convert into an electrical system by using the analogy between these two equations. So, that is why it is called a force F current I analogy, force current analogy. So, force is to current, both are independent variables. Then what are the dependent variables? I say here x is the displacement and correspondingly flux is the parameter in electrical system. Then x dot means it is a velocity, it is voltage. So, these two are dependent variables of a mechanical system and corresponding electrical systems. Now, when you compare the mass of a mechanical system, it is capacitance here. So, if the mass of given some parameter, that should be transformed into capacitance of same number of farads for analysis in electrical system. That is the meaning of force current or force voltage analogy. Similarly, you have a friction B here, that is 1 by R in the case of current analogy, and K here the spring stiffness constant K, and you have here 1 by L. So, this is the way analogy can be developed if equations are being written very easily. So, which law again? Here, as I said, Newton's second law of motion is being used to write the equation, and here we use KCL, unlike KVL in force voltage analogy. So, that way you must be thorough with the basic laws or basic principles to write the required equations. Applying Laplace transformation and getting transfer function is very easy. Now, once the awareness of translational systems, is being discussed, if you are familiar to these translational and electrical systems, now rotational systems also very easy to understand. As I said, in translational system, when you have a force that is applied on a mechanical translational system, the corresponding term in rotational system, it is a fixed axis rotation system. Please remember, rotational system means which has fixed axis rotation. So, torque is the term, independent variable that appear in rotational system, and in electrical system we say it is a voltage. Now, the dependent variable in electrical system is charge or current. I said here linear displacement and velocity. In the case of a rotational system, fixed axis rotation, it is not a linear displacement, but it is an angular displacement. So, in rotational system you have angular displacement as a output. Theta, it is represented by theta, the angular displacement, and angular velocity, it is a linear velocity represented by v, but this is angular velocity, it is represented by omega, that is theta dot. So, the units are radians here, this is radians per second, whereas linear displacement is meters and velocity is meters per second. So, that is the only difference. You have a fixed axis rotation, so angular displacement, angular velocity, angular acceleration. Now, if you see the passive components of system, like you have L, you have C, storage components, and resistor. We have already seen here mass, then 1 by K spring stiffness, and R is corresponding to friction in a translational system. So, here instead of mass we represent here J, this is nothing but moment of inertia. Moment of inertia, the weight of a rotational system is represented by moment of inertia J. Now, spring stiffness, it exists even here also, but it is a rotational spring stiffness constant, and friction exists even here also, like B. So, the equation when we have written for force m d square x by dt square plus b dx by dt plus kx in a mechanical system, here torque is the force applied in rotational system. So, it is J d square theta by dt square, angular acceleration term, then B d theta by dt, velocity term, this is angular velocity term in radians per second, plus k into theta. So, very easy to remember, you can see that force and here it is a torque, displacement of linear, but here angular displacement. And this equation anyway we have seen just now, V is equal to L d square q by dt square plus R dq by dt plus 1 by C into q. So, this is the way torque voltage analogy can be developed, and then any given mechanical system can be analyzed in our convenient way in a electrical systems laboratory by transforming those parameters into electrical parameters with the help of analogy. Good number of questions can be generated using these three topics, and then you can actually solve any problem if you are able to solve basic laws. Using basic laws, the given mechanical system.